It's my real pleasure to introduce Dr. Mary Bourke from Trinity College, Dublin. Used to work with us. Very sadly, we lost her to, first of all, the Planetary Sciences Institute in Arizona and then to Trinity College. But we're really grateful to have you back, Mary. Mary is a polymath. She works on all sorts of geomorphological topics on Mars and on Earth and probably on other planets and planetary bodies. But I think you're largely going to talk about Earth with a bit of both. Bit of both. Excellent. So anyway, take it away, Mary.
Thank you very much. Hi everyone. It's great to be back. Great to be here. And so what I'm going to do really, the point really of me wanting to come here, is to introduce to you what a relatively new research group in Trinity College in Dublin in the Geography Department is trying to achieve. We're about 3 years old. And I just want to basically show you some of the work that we're doing and hopefully be able to come back in future years and present more advanced knowledge. So the title of my talk is to look at the response of rockscapes to extreme events and in extreme environments. And this is definitely one of the areas of research that I am passionate about. Probably because, if I'm truthful, back in the day I was only really excited about things that I could, at the human timescale, see changing in front of me in terms of geomorphological systems. So when we had big events, sorry, the perturbator's coughs in the audience. That has continued.
It'd be really irritating.
I get the message. That continues on throughout my whole career. So I'm going to start first by taking you to another planet, an extreme environment that has had a lot of data collected about it, the planet Mars. It is a very interesting planet. A lot of people think it has a lot of analogies to Earth. In its early history, it's thought to have had a thick atmosphere that was able to have a hydrological cycle. So we had perhaps oceans, rivers, lakes, etc., high rates of rock weathering, and a lot of processes that are similar to those today. And then we had catastrophic climate change on that planet. We had the loss of the magnetic field because the core of the planet cooled down, and so the atmosphere got eroded away over a long period of time, and we went from what many people think is a warm and a humid climate into a cold and arid one. But one of the most kind of mega geomorphic features on this planetary surface is impact craters. And so here is one of these ones from Mars, and they're certainly one of the oldest recognizable large landforms on the planet. We also have very large volcanoes and tectonic structures as well. But impact craters are a very important geological process right across our solar system, right across every single body in our solar system has been impacted by these. So we can see examples from Mars, from Moon, Mickey Mouse here on Mercury. Venus here looks a little bit different because, of course, we have to use radar technology. The atmosphere on Venus is so thick that the optical part of the spectrum doesn't penetrate. And, of course, Earth giving itself away here because of the vegetation in the center. So we have a lot of these planetary bodies that have a very cratered surface. It's a very important structural control, topographic control. But, of course, for example, we have here 635 craters, 35,000 craters on the surface of Mars that have been documented, whereas only 188 confirmed ones on the planet Earth. And of course, this has to do with the fact that Earth has this plate tectonics phenomenon, which is the only place so far in our solar system where plate tectonics has been identified. And also, we have a very vigorous weathering environment. And they're important because really it's how mountains get built in our solar system. If you look at these very large impact basins, you can see that the mountain rings rise up to 2 to 5 kilometers in these rings around the central area of the crater. And so this is a question I like to give to my students. They hate it because they want to talk about the other normal earthbound processes of mountain building. And so this would have been part of the phase of Earth where our mountains on Earth would have been built by these impact craters as well. So I have brought with us some analog glasses, and we're going to show you now a sequence of, I think it's 8 images of impact craters on Mars. And so the correct way to wear your glasses is to have the blue, mine are all fogged up now.
Oh, I got them the wrong way around.
Well, trial and error. If it's not popping out. Yeah. So the blue on the right works for me.
Oh, yes.
And so these are anaglyph glasses, and basically these are just red, green, and blue bands and images which are physically separated to give you this 3D perspective. And so here is your crater rim. Your ejector sheet is faintly visible externally to it. And this is an unusual pair of craters because it has a pit in the centre. And on Mars, that's supposed to indicate that the surface into which the missile impacted had a lot of volatiles in it, perhaps frozen ice in the subsurface. So you have quite an explosive impact happening here, and then collapse of what might have been a central peak. And then you can see here all of these mass wasting features around the crater, which have slipped down in the final modification stage of the crater formation. I'm just going to show you a few more of these. This is okay.
We're easily pleased.
I'm so glad.
Thursday afternoon, it's just what we needed.
I know. So here we have what would be called a simple crater. So the smaller craters tend to have a more simple morphology, a bowl-shaped morphology without a central peak. And you can see here that there's evidence of mobilization of materials down from the crater edge down into the center of the crater. So these would be, again, mass movement. And of course, the gravity on Mars is 1/3 that of Earth, but we still get mass movement and gravity-driven processes operating on this planet. So we'll move on. This would be great for Halloween, wouldn't it?
Is that a pumpkin?
Exactly. So this image I'm putting up to show you the antiquity of the surface of Mars. So that while a lot of these craters might look like they're relatively fresh and almost pristine, we do have a very ancient surface on Mars that has been buried and then re-exposed or re-exhumed, most likely by aeolian processes. Aeolian processes are now the driver of most of the surface geomorphology on Mars today. So impact craters eject material from the site that they impact. And what you're looking at now is a gentle slope up to the rim of the crater from the outside towards the inside. And you're looking at the ejecta sitting on that ejecta blanket. And these would be ancient. These rocks, I don't know exactly how old this crater is, but we're talking billions of years. Billions of years of sitting in this place, being exposed to weathering conditions on the surface of Mars. And so many, many years ago when I was here, I remember talking to Heather about this idea of like, well, how do impact blocks break down? I mean, what is the driving force that controls around it? And we can see here that we've clearly got some ventifacts, so aeolian processes, sandblasting will dominate. But we also have fractured rocks with cracks in them, or rocks that look like they've been broken apart. So clearly there's a fracture set that's involved in the breakdown of these particular rocks. So here is looking at a sand drape. This is probably a small ripple feature taken by one of the rovers, again showing this interaction of the gravelly floor with this abundant sand material in some places. And of course, this looks very familiar to the people in this room who work in desert areas, these areas of ventifacts and sharp stones. And if only they had had a geomorphologist on the Curiosity rover team, they would have benefited from the knowledge that if you want to drive your rover over these plains, they'll puncture your tires on Earth and they will not puncture, but they will drive holes in your wheels of your Curiosity rover on Mars, and that's exactly what's happened. This image here is the last one, I think, of the anaglyphs that I'll show you. And I love it because this was taken by a rover, and it's a view across a crater looking at some of the ejecta on the crater. And I want to draw your attention to the fact that this is a beautifully aeolianly eroded, a rock that has been eroded by aeolian processes with grooves and flutes on the side of it. So that's the end of the anaglyphs. I'm sorry. So let's talk about impact cratering. It's a three-stage process. First of all, you've got your impact, your compression stage, then we have an excavation stage, and we have a modification stage. So this is basically what's going on when you have your target lithology, you have a meteorite come in and impact it. You have, first of all, if we look at this side, you're looking at the shock pressure contours that goes through the crust as a result of the impact. Obviously the highest ones here, 50, 25, down to 1 gigapascals of shock pressure moving through the subsurface. And although this is a cartoon, it does illustrate quite well what the response of the rock is to that. So you're getting melt here, shock metamorphism here, and then fracturing and brecciation further away. So what's really interesting about this, you'll remember already that I've told you that impact craters build mountains on planetary systems. This takes seconds. Seconds for mountains to be built on planetary surfaces. It's really quite a remarkable geological process. So we have already looked at some of the morphologies of the craters themselves, but the rocks hold a story. They also change with distance along this shock boundary, with distance from the centre of the impact. And you get a whole range of different rock types that have been very well identified, from impact breccia through shatter cones, hydrothermal stones, or the result of the hydrothermal activity is also found, particularly if you have these impacts into volatile sources. Tektites driven up into the atmosphere again and become melt products as they enter back in through the atmosphere, back down onto the surface. This signature is not only held at the landform scale, at the whole rock scale, but also at the mineral scale. And actually this identification of shocked quartz ended up being really, really crucial to proving the identity of several of the impact craters on our planet. This idea of shocked quartz, where you can see these intersecting shock laminae that are a result of the shock waves going out from the impactor and then returning back in to the center of the crater, where we get this lift up happening in terms of landforms, but the minerals themselves retain this shock message. And it was the discovery of this as a signature of the impact process that allowed a lot of the features that were being thought to be perhaps volcanic structures to be impact structures. So, rocks suffer greatly from impact, and we find that a lot of impact craters on Earth end up being hard to recognize. This is from North Canada, and we can see here that an outline of proposed and confirmed impact crater that is now only identified by those various shatter cones and those other geological signatures that have been identified. So the idea that impact craters break down on this planet hasn't really been studied at the level of landform, rock and mineral that we would like. It's not been knitted together in a suitable way, in a geomorphological way. So lots of people have described the entire landform and how it's often modified on many planets by gravity, on Earth by gully systems. John Grant, Mick Schultz, David Kring, Matt Golombek have all done some really, really good work. But nobody has examined how impact might affect the rate in which, or the style in which, the individual rocks break down. And so one of my students, Ankit Verma, who is now coming into the last year of his PhD, has decided to take this on board, has decided to look into, at that rock scale and that mineral scale, what happens to weathering products in this kind of regime. And so he decided to go to a relatively young, relatively pristine impact crater, one that was formed 50,000 years ago in Arizona. It's a semi-arid climate. It was formed by an impactor that was thought to be 30 to 40 meters in size, and was the training ground for a lot of the Apollo astronauts before they went to the moon. So this is an image from Mars. This is an image of Victoria Crater from Mars. So one of the points is that we love them on Mars because they give us this access without a drill core or excavation to the subsurface geology. And so what you're actually looking at here in the wall of this crater is an aeolianite. But what I want you to see, apart from the beautiful bedding, are the fractures. Complete shattered facies here throughout this whole section. And so that is what we might expect to happen in sandstone targets here on Earth. So this is the site that Ankit is studying, looking at the inside of the crater wall here. We've got 3 different formations that are in evidence here. We've got the Coconino sandstone, the Kaibab limestone, and the Moenkopi sandstone. And the approach that we've taken is basically to use this crater as a place where we can go and look for the impact of impact. And then we want to find control sites. So we've gone to sites that have the exact same facies and lithologies, but were not under the same amount of impact shock, but have been exposed to the same climate. And we've looked at sites here and compared them to this site here. Now, it's a sandstone target. There's not a lot of sandstone targets on Mars, but there are some. But Ankit has put together this wonderful, basically graphic from an annoyingly dense table to basically indicate that as shock pressure, we're going from 0 through 5, 10, 20, up to 60 gigapascals, you're getting a different expression at the mineral scale here of different features. And so Ankit has basically started out by looking at low shock rocks that fall in this area here from the Meteor Crater in Arizona. And I anticipate that he will basically spend a lot of his career moving along this axis here to look at higher and higher shock impacts to see how we're finding the relationship with rock breakdown. And so here is actually not a slide that was produced by Ankit, but this is from Bevan French, who was the professor who discovered those crossing lamellae in the quartz. And so this is from his wonderful book Traces of a Catastrophe. And so on the left here we've got that Coconino sandstone, which is pure, almost pure quartz sandstone. It's very brittle and pure white almost in colour in the field. And we can see here evidence of pore spaces and cements surrounding the quartz grains. And this here is an example of the exact same lithology which has been shocked. And this is to visually show you that the quartz grains themselves become dissected with all of these fractures as a direct result of the shock environment. If we look in a different formation, here we're looking at the Moenkopi sandstone. And again, Ankit has done some work looking at these images of unshocked and shocked. And so the difference we see here is the pore spaces, which are the dark in the unshocked on the left, are gone in the right. So what we're looking at is in a low shock environment, a shock environment of less than these 5 gigapascals, the porosity of the rock is reduced. Now, porosity is incredibly important in a weathering environment, particularly one that has humidity involved. Again, there are no shock features to look at the fracturing in quartz grains in the Moenkopi, but here is again a shocked one where you can see the fractures distributed through it. Ankit has also pioneered this X-ray CT scanning approach at this scale for weathering studies. And so what you're looking at here is a very small section taken at, these are slices taken at 10 microns per pixel resolution, and we've got this fracture system here, and here it is in 3D. And so he's developing at the moment analysis routines whereby these fractures can be quantified. And I think this will become an incredibly important methodology, particularly for experimental work, where we're looking at the before and after in experimental routines where we're putting our rocks into experimental cabinets. So these are the rock breakdown features that are typical of the Moenkopi sandstone that we find in the field. We've got flaking and alveoli development, entire block disintegration through fracturing, a lot of granular disintegration deposits on the floor underneath these rocks. And so Ankit was interested in documenting the morphologies and quantifying them. So he undertook high-resolution, close-range photogrammetry of many, many rocks in this Arizona site to apply structure for motion and build DTM models. And so here is one of the DTMs that he's built, and what's innovative about what he's done. I've to date only read papers that use structure for motion for landscape or landform scales, and the innovation that Ankit is bringing is that he's actually bringing it down to the sub-millimeter scale. And he's using a camera, and he's using a target, and that's all the equipment he needed. And I think that is huge, because we work in areas that are highly inaccessible, and he himself had to scale these very steep slopes on the inner side of the impact crater. And so then he was trying to develop these analysis routines. Looking at a range of parameters, he was analysing these DTMs. And so he's looking here at the maximum height of the surface. And what is incredibly disappointing for me is when he compares the meteor crater rocks to 3 different control sites, there's no statistical difference, either in this morphometric parameter, or in slope variability, or in fractional dimension, or indeed in feature classification. No significant difference. And this is an issue that's plagued interests of mine for actually almost a decade now, is how can we quantify these rock breakdown, effectively quantify these rock breakdown features. Even in rock hardness, we don't see any significant difference between the shocked rocks and the unshocked rocks. So what Ankit is now concluding is that for low shock environments, those environments that have less than 5 gigapascals of pressure that have gone through them, we're not seeing any measurable difference in the way in which rocks break down. And so he's now going to continue his interest and continue his work by moving up a shock classification and finding sites, for example, Lonar Crater in India, where he has access to samples that do have a much higher shock recorded in them, and to run a suite of experiments that he's developed, and a suite of routines here, analysis routines, and to see if we can pick it up at a higher shock level. So I anticipate great things for Ankit. I think he's been incredibly innovative in his approach so far, and I do think that he's found a niche and a market for himself in the planetary field. So I want to change gear a little bit and come down to earth. I want to talk about the coastline of Ireland. If you take a measuring tape that's 100 meters in length, you will realize that the length of the coast is over 5,000 kilometers long. And that's because, even though for a small island, it's a highly irregular coastline with a lot of bays. It's a rocky coastline for a lot of it, but it also has a huge number of quaternary cliffs that are supplying sediment, and also composite cliffs. Some are quaternary sediments overlying bedrock. But the geomorphological nature of the coastline is not well described, because most of our geomorphologists have worked on the soft coastlines and not on the rock coastlines. And so, why should we care? Well, the projections both for your island and for my island in terms of future climate change are not good. We're looking at a wave climate that's going to increase in both its magnitude and its frequency. And so there is a need to understand how our coastlines are responding to these extreme events. We've got, in the most recent census, 40% of the population of Ireland live very close to the coastline. And so we have these cliffed coastlines, but we also have coastlines with rock platforms on them. And so a research question we had in our group was, well, what is the role of these platforms to protect our coastal areas? And so the idea is that you will have a certain amount of wave attenuation as the waves break over these rock surfaces as they approach the cliff lines, which are heavily populated. And so for those of you who are not from the coastal area of geomorphology, this is a coastal platform in Lahinch on the west coast of Ireland, and the definition that we have available to is that it's a continuous shore-attached bedrock surface which truncates the hinterland topography. And I went out into the field with this definition and looked for these features, and I couldn't find a lot of them. What I also found was classifications by Tsunomura from his book in 1992, where he had, in terms of platforms, defined two types: platform type A, which is a ramp, and platform type B, which is a bench fronted by a cliff. And a lot of people have, certainly in the earlier stages, based their understanding of coastlines around this classification, but also tried to understand what role, for example, tides had in developing these kinds of platforms. And so I went to a chapter that was published, written by Cherith Moses in 2014, to try and find out. I think it was entitled something like Coastal Platforms of Britain and Ireland, or the British Isles, or something like that. And this was a map that she pulled together from literature. And the dark black lines are areas of known coastal platforms in Ireland. And I was down here. Lahinch, I just showed you. It's not on this map. So we had to basically start off by trying to produce a map of where coastal platforms are in Ireland. And luckily we got sponsored by the Geological Survey of Ireland to do this. And we had a whole team working with us of Italian interns, undergraduates, postdocs, Larissa Naylor from University of Glasgow, Kieran Nash, who's here now at Oxford, and myself and Niamh Cullen. And we hit a bump in our first attempt. And it's always the same with geomorphology. Mapping is one of the hardest things. Where are you drawing that line, and how confident are you about that line? And in a dynamic environment, which on a diurnal scale has a changing boundary, we had difficulty, according to the published definition, of identifying the full extent of platforms. For example, this is a detached area of bedrock. Is this not part of the platform? Look through the water, we can see all of these clearly bedrock outcrops. Where do I put my line on this map? Okay, challenging. And so it's starting to bring to mind this idea that perhaps the definitions, which by their very nature are quite restrictive, may need to be revisited again. We decided we were going to use the best data available to us, which was satellite data. So we set about a program of mapping from remotely sensed data, drawing polygons, and we decided to have the same error for all of our data sets, which was we just mapped what was above the water. We couldn't interpret this. I don't know how much of this is seaweed and how much of this is rock. I don't have that technology available to me. And so what we ended up producing was a data set that certainly identified the location, but not the extent of the coastal platforms. And so we've mapped them. We give them a confidence level, or do we really believe that that is a platform, or do we need to double check that? And then we selected a number, 30% of them, blind validated them, got another team to map them again, and then we went into the field and we validated them. And so we ended up with a much more complete map of the location of platforms around Ireland. And this is one that we continue to validate because, as I said, it's a 5,000 long kilometre coastline. So that takes a long time to get to all of these areas. But now at least we have this, that we now have a basis to launch future inquiries. But some of the stuff we found kind of was a little bit troubling, and maybe the quaternarists in the audience will be able to speak a little bit about this, because you'll remember that platforms truncate the hinterland topography. In other words, that they always have cliffs behind them. More of our platforms, you can see here on this diagram here, more than 3,500 of them had no cliffs backing them. And this is clearly an inheritance problem from the glacial scouring of the landscape multiple times across Ireland. It may be something else, but it needs looking into. Some of them have protective covering, some of them have large boulders sourced locally from the quaternary sediments, and here's Larissa Naylor here in her jolly white wellies, jumping over these boulders with glee as she does in the field, looking and wondering about these, whether or not they're protecting the platforms or whether they're contributing to the erosion of the platforms. And here are images of the platforms that we came across. So the majority of platforms are from sandstone fascies in Ireland, and I'm not seeing any gently sloping ramps here. I'm seeing upturned bedded sediments of various steep degrees, stepped. Here's one from the Aran Islands, all around the west coast. When we looked more closely, we could see that the surface morphology was highly variable. And if you go back to the original question, is what is the potential for platforms to attenuate wave energy? This becomes important, this surface morphology. The presence of these huge channels, whether or not they're significantly bio-eroded on the limestone in the burn, whether there's these pinnacle or channel features which are over 1.5 meters deep. Here's Alex Scullion here for scale. And so, sorry about the words, you don't have to pay any attention to it necessarily, other than saying we're coming up with a new classification. A new classification that will complement this one, and it's based on this idea around the surface geomorphology of the platforms themselves. Looking at whether they do need to be attached or unattached, whether they have a cliff or not, and what is the scale of all of these surface features. But we're interested not only in this qualitative description, but what we also need to do is bring it into a quantifiable regime. And so here we're deploying our drone across many, many coastal areas. One, to benchmark them, so we have a data set for the next time we get a large event. And secondly, to build digital terrain models of the features. So here we are in County Cork, and we collected as a pilot study detailed DMs of 2 locations, 2 juxtaposed platforms that are exposed here at A and B. And they're very, very different in their presentation at the coast. We can see here one that has quite a large roughness and one relatively does not. And we were able to build DEMs with resolutions of in the centimetre scale. And then we wanted to try and analyse them in some way to develop a parameter that we could actually distinguish these very rough ones from the very smooth ones. But also build up this DEM where we can then roll out wave models over these platform surfaces to test just how much there is attenuation of wave energy across these surfaces. And so that's where we're at the moment. Very pleased to say that last week the Geological Survey of Ireland said, okay, we'll give you a little bit more money, go ahead and pursue this. So next year we're going to roll out this approach on many, many more of the platforms, trying to pair off the qualitative classification with the quantitative DEM production to see if we can get a signature that can be applied nationally by the Geological Agency in modelling wave attenuation. But what we really want to understand is the response of these platforms and these cliffs to extreme events. And in recent history, and this is really one of the reasons why I've got so interested in these coastal rock landforms, is we've been hammered. We've been absolutely hammered in the last few years by these extreme events, these extratropical cyclones, these degraded depressions hitting the west coast of Ireland, which is the island of the continent of Europe. We are the first gate to all of these extreme events coming in off the ocean. So for example, in 2016 we had Henry, Imogen and Jake, all happening in February and early March of 2016. The significant wave height, which is the top third of the waves, 11, 13 and 6.7, but look at the maximum wave height, 21 and 23 meters high. Big systems coming in with lots of energy. And so Niamh is working on this particular site here down in County Clare, Ballard Bay, and we visited it after these storms in 2016, and we noticed on the surface these markings here, which are essentially tool marks. They're formed by clasts being dragged across the surface of the platform. And this particular one here in this image is a single clast that has the 2 outer edges of it that have scratched the surface of the platform. And so we've adopted Richardson-Carling's terminology here. They looked at bedrock canyons to look at these features we're finding in County Clare. And so Niamh went into the field and she basically, following the 2016 storms, identified these abrasion trails, as they've been referred to in the literature, and mapped their the movement of the blocks at the time of the storm. She went down shortly after this. And she then selected a subset of these because people have noted that clasts can abrade the platform surface, but this has not been quantified. We don't know if they're effective geomorphic agents. They don't seem to be. There seem to be these shallow little striations, or some of these percussion marks where you've got impact of large clasts on the edge of the sandstone here, knocking off chips. And so for her thesis, a part of it, Niamh has basically meticulously, as some PhD students do, gone out and measured the surface area of 2,000 striations. God bless us. Because there is a need to quantify whether or not this is important. Should we be paying any attention to it? And not only did she do that, but again she used the structure from motion at the very high resolution to build DTMs of the percussion marks, so the volume of material could be calculated. And so we applied the data that we got up to all of the measured averages, and applied it to all of the measured clast abrasion trails, and came out with figures in the area of maybe, when we combine them all together, 17 meters squared of abrasion, where actually that's the figure for the entire surface at that time. So it's not a lot. And then we wondered, well, is this a process that just happens during the big events? They are definitely signatures of catastrophic events, but it is only the storms that move these boulders and have this geomorphic process going on. So we set up a series of boulder experiments. Here's one where we laid out clasts that Niamh carried down herself. The experiment was only limited by what she could carry, which turned out to be 17.5 kilograms, from her car, which is actually parked a mile up here, down onto the platform. And she left them out during just a normal spring tide. Let's see what happens. She had a pressure transducer installed here that Larissa Naylor from Glasgow had lent us, and she ran the experiment for 24 hours. Now, this is not her experiment. This is one we did with some students in the field just this September. But this is similar to what what she did. So here's a calibrated pole. This was just for the students so they could reconstruct wave height. But here are the actual boulders that the students deployed, and they're much bigger than we had. A couple of hefty lads with us, so they were able to carry a 50 kilogram boulder down onto the platform for this one. And here is a drone image of, keep your eye on now on number 18 there, who's going to win the base. And so we flew the drone for 13 minutes over this, and we managed to catch these blocks being moved by just normal spring tide this September. Massive big blocks. And so, and this is not in any way accurate because this is all new data, and there was drift in the drone as it was being blown by the wind. This is, over those 13 minutes of the video, this is kind of where the blocks moved from and to, from and to, from and to. So moving around the surface of the platform. Okay, so clasts get transported, right? Okay, so we've shown that big clasts can get transported under normal conditions. But in Niamh's study, what she was able to show was that they had a geomorphic effect. So here are the big storms that scratched away that platform in her first data set compared to the wave height, much smaller wave height, and still we can see a geomorphic effect. Again, little scratches, who cares? You know, really, is it that important? Once you get your eye in geomorphology, once you know what you're looking for, the entire platform is a palimpsest of these scratch and abrasion marks. The entire platform. You can see them everywhere. Overlaying each other, some of them get colonized by lichen very, very quickly. We think it's about one season, in fact. It's a lovely little study to be done there in terms of the type of lichen that's colonizing these features. And so if you think of this process then over a significantly long enough period, and so we've had stabilization of sea level pretty much for several thousand years here on the west of Ireland, and we have this process here, we think, going on, scratching away like a cheese grater over the surface of these platforms. And so there's very few clasts on the platform. Some of them come from the platform themselves and are plucked out and are scratching it. Others collapse down from the cliff. And so now we have this coupling of sediment supply between the cliff and the platform and the geomorphic effect that's measurable from it. We would begin now to say that this is a process that needs to be considered in platform evolution models when you're considering the evolution of them over the millennia. And we would also want to caution people who are beginning to apply cosmogenic dating techniques to date platform recession. If you have this constant abrasion at the microscale, at the sand grain scale almost, going on and being effective, I'm not sure that I can trust this technique any longer. But Ireland has been subjected to extreme events. We have an extreme wave climate. So O'Brien and the group at University College Dublin have put together a lovely catalogue from historical sources and reports of all of the big waves that have hit Ireland, and have classified them into storm waves, tsunamis, and of course these rogue waves, which we know about in modern Ireland because so often fishermen and fisherwomen are getting just drowned out to sea at certain locations by these rogue waves that are coming in. It's a real hazard. But for me, I was like, wow, 12 tsunamis. That's, you know, I didn't know I knew. I'd heard about the Lisbon one, I'd heard about some ideas around the Aran Islands, but 12 tsunamis in this history, that's pretty interesting in terms of thinking about what set up our coastline and configured it into its shape at the moment. And so it's interesting for us to kind of look at this historical trail. The night of the big wind is the first documented hurricane scale winds that have hit Ireland. And this was truly a horrific episode. At that time in 1839, we had very much a rural farming community. They lived in thatched cottages. This was what's known as Little Christmas, the 6th of January, where families were basically going to each other's thatched cottages for socialising. It's known as Little Christmas or Women's Christmas traditionally. And they went about their day. It was a warm day, and at 3 o'clock in the morning suddenly they heard the howling wind, and this is documented across the country in Ireland because in the years following, it was in 1837 and 1839, they had all of the oldest children in the schools try to collect stories from the oldest members of their family, the folklore, and they all spoke. We have a great documented description of this wind, and it was truly horrific apparently, and it was truly devastating. There was no place in Ireland that was not affected by this. So the families went to bed and they were woken up by these massive hurricane speed winds, and it blew off the roofs of the thatched cottages. It sent winds down the chimneys of the thatched cottages that fanned the embers and set the thatched cottages on fire. The families children, babies had to leave their homes in a hurricane with no shelter. There are recordings of them bending down and holding onto reeds to stabilize themselves. They were terrified their babies were going to get blown away, so they put them in any kind of contraption, put rocks on them to keep them stable. The death toll is around 300, but of course in those days any injuries would not have been able to be medically treated, so people would have died from broken bones, head injuries, etc. So the death toll could be something up to 500 at least. But of course Ireland and the UK has had hurricane winds, not hurricanes. We don't get hurricanes. They lose their eye before they reach our islands because of the cool water temperatures. But we still get these hurricane winds. For example, the one we had last month, Ophelia, were recorded of 191 kilometres per hour at the Fastnet lighthouse down here. And it certainly shook up Ireland in many, many ways. We're not used to having hurricanes, and we're not used to having to develop a social policy whereby we have potential evacuations or country-wide declarations of behaviour that would improve the safety of the people. So the warning was a weather warning, and the entire country was categorised as a red alert. Okay? the entire country shut down during Ophelia. Now, we were told that we had to keep our children home from school to keep them safe. And we did. But perhaps that was a questionable outcome. And also, there might be a little bit of confusion about what the impact of a hurricane might actually mean for Ireland. And of course, having Auntie Mary as a geomorphologist calling you to say, pin down the cows, get the children inside. So we sent a video on WhatsApp by your sister of your 3 nephews having great crack all together. And really, I mean, I suppose the message from here, other than the pure joy of children, is compare the experience of these 3 young lads to the experience of the children during the night of the big wind. These lads knew what was happening. Their Auntie Mary had told them exactly what was happening and what they should do. Now, they disregarded my advice completely. But back in the time of the night of the big wind, these children would have thought that the fairies were rising up and there was retribution happening, because at that time Ireland was a very spiritual country. So Ophelia created a huge wave sequence that bashed the coast of Ireland. Here we have it fascinate again, this 17.8 one. Now this is from a newspaper, so that's why we've now got a category of monster waves apparently, in addition to rogue waves. So it would be interesting to see what the geomorphic response for that was. And by complete coincidence, and we'll end up on this little story here, I was on my summer holidays and I went down to Niamh site and I took this picture, just checking everything was okay and what had changed. And so I do have a record here of rock falls. I went again with my 4th year field school, and we came across this very large rock fall that had come down in that intervening period, and that was taken on September 22nd. And we set up a time-lapse camera here, saying, okay, well, let's watch to see, you know, how long it takes for this supply of sediment in this sediment-limited system to actually be removed. And so here is a sequence of images that were taken at that field trip in September. And then Niamh ran down to take other data, and we flew the drones, so we all have all the, haven't done it yet because it's so recent, but we're going to build DTM and quantify this. But Ophelia managed to remove some of the material, but a lot of the material was left behind. But it was a subsequent storm, Storm Brian, that actually finally removed it all. And the reason for this is that Ophelia, even though it was a much larger event, you remember the maximum waves were in the 20s of metres, and Brian's were in the 11 to 13, was the direction of the winds and the direction of the waves. They were not right on into the bay here. They were actually at an angle, and for a lot of the storm, the winds were actually offshore, whereas for Brian, it got hit straight on. So the idea of matching the magnitude of these coastal storms to the geomorphic effects is not clearly not such a simple relationship. So these are some of the team that have helped us in the field. There's Niamh on the left, and Kieran and Archie and little Cueva, who's great in the field. And so that's it for my lecture. I'm happy to take any questions.